Hello, I am Adina Edwards.
I'm Galen White.
And I'm Hannah Stepanek. A car spends an average of 60 seconds waiting at a light. Implementing a video-triggered traffic light system on a field programmable gate array, more commonly known as an FPGA, would severely reduce time wasted waiting for red lights. Gas efficiency for city driving would be improved regardless of the year, model, or condition of the vehicle. We will provide an overview of the block diagram, along with each block's corresponding engineering requirements, explain how the system will be tested, discuss some unique design concerns, and provide a list of future work. But first, we will give you an overview of how image processing, more commonly done in software, can be implemented in hardware.
Performing image processing on a piece of hardware like an FPGA can seem counterintuitive to those who use programs such as Photoshop. Since images coming into a computer system are originally real-life data converted into electrical data, electrically triggered hardware like an FPGA can complete the processing without having to reinterpret the data in a format readable by software. Images are a series of matrices full of numbers representing light at each pinpoint-sized area of the image. By doing specific combinations of basic arithmetic like addition and subtraction many times over different parts of an image, we can process an image without the complication of software. Low-level hardware involving digital logic gates and groups of transistors can perform these simple additions and subtractions based on physical and electrical properties of the numbers represented in the image matrices. This makes image processing on hardware much faster and uses resources more effectively than doing the same processing in software.
Presented here is the top-level block diagram. Light in represents the light reflecting from the real-world objects into the cameras to produce 4 video streams. Wind velocity represents the force of wind on the cameras, which will cause jitter in the video. One of our unique design concerns is that this may cause too much movement in the image processing block and distort the data. While power powers the system, light out represents the light from the traffic light simulation boards. Here's the system-level block diagram, which we will now cover in detail. First, we will take a quick look at how the system is powered. The system takes in standard North American well power, converts it to a 12-volt DC signal, which is then received by the system's power board and distributed to the FPGA and Atom processor at 5 and 12 volts DC, respectively. Though routed through the Atom, this will also power the USB cameras. 4 USB cameras will be used in this project, corresponding to the 4 directions of traffic. The FPGA Atom hardware unit has a limited number of USB ports, so a USB hub will be needed to interface with all the cameras. These cameras were chosen because of their many standardized features. USB is a widely used protocol which interacts well with the generic video drivers, and the film rate is a standard 30 frames per second. Note that the system must be able to make out a car from at least 50 feet away. Next, we will take a look at the Atom and how it controls the traffic lights. The Atom will receive pixel coordinates and the number of cars for each direction from the FPGA and send an interrupt to the traffic light simulation boards indicating that the light should change. This data will then be used to calculate when each car will arrive at the intersection, ultimately deciding when to change the light and flow with traffic. The traffic light simulation board will be run on 4 Wonderboard units that will simulate normal traffic lights. If there is an equal number of cars approaching from all directions, the cars that will reach the light first get to go through the light first. Here's an example. Note that the cars approaching from the left are traveling faster than the cars approaching from the top of the screen. This time, watch the light. Note that the light transitions to let the cars go from the left before letting the cars go from the top. The light will also transition to allow the greatest number of cars possible through the intersection. Here's an example. Note that the 2 cars are approaching the light from the left side of the screen, and 1 car is approaching from the top.
The algorithm uses
Watch the light this time and note how it transitions to let the 2 cars from the left pass through the intersection before the single car.
If something happens to the camera feed, or the camera lens, so that it cannot determine the traffic approaching the light, the traffic light will default to a timed intersection.
Next, we will examine the FPGA and image processing algorithm in more detail. The video is passed into the FPGA from the Atom via PCI Express in the form of 2 consecutive grayscale bitmap frames. Then the 2 images are passed through a filter, converted to black and white based on a contrast value, compared, and the car is found. And finally, the location of the car is passed back to the Atom via PCI Express. This entire process will be pipelined, meaning 2 frames from each of the 4 cameras can be processed at once. The filter, which is calibrated automatically during initial system setup, is run on both images. Essentially, it crops the image so that the only thing left to process is the road. This helps increase performance and decrease power. Next, the contrast is calculated by finding the mean pixel value and used to convert the images to black and white. The contrast is the most important part of the image processing. Presented here is the same image with different contrast values. As one can see from the examples, the difference in the appearance of the image is vast. Next, the 2 images are exclusively ORed together, pixel by pixel. The resulting image, as seen here, turns white wherever there is a difference in pixel value indicating movement. Notice that the movement from the bushes and trees in the background is also picked up by this algorithm. Most of this noise is filtered out by the filter stage, and the rest is small enough that it can be ignored when searching the image for the car. The system must filter out this noise so that it does not accidentally trigger the light. In the final stage, a row column coordinate centered on the car is chosen and sent to the Atom via PCI Express.
As per the engineering requirement shown, the algorithm used for image processing must be able to recognize a car at all hours of the day. The algorithm must also be able to handle glare from rain on the road.
We are in the process
and not
of
mistake the
installing
glare
the
of a car's
camera
headlights
video
as a
driver
separate
onto
vehicle.
the system and verifying its
Since the
function.
traffic light system is intended for real-world use, there is always a chance of something going wrong.
We
The
also
battery
need to
backup
decide
system
how the
is
system
designed to
should be
minimize
tested.
problems when they arise.
Ideally, we would like
The
to set
problem
it
can
up
be
and test
categorized
it
by
on
a
an
lack of
intersection on
communication
campus.
between the Atom
However,
processor and
if
the
this is
simulation
not possible,
or
we will
erroneous
most likely
data
use
sent from
toy
the
cars
Atom.
to simulate traffic.
By another engineering
Now that you have watched this
requirement,
presentation,
if
you should
communication
understand
is
how
cut
image
between the
processing
Atom
can be
processor
implemented
and the
in
traffic
software.
light simulation
Some of the
board,
main engineering
the battery
requirements
backup
for
is
this
used to power the
project,
traffic
basic
lights in a way
functionality
that
of each of
safely
the
directs
blocks,
traffic
some unique
is
design
familiar
concerns,
to
and the work we
drivers.
still need to do.
In this case,
When this project is
lights in
finished,
all
we hope to
directions
have
will
a
flash
viable
red,
prototype
as is the current protocol for power outages.
light control
It is
systems.
important that the whole system be easily testable. We will have an external display connected to the FPGA so we can easily verify the image processing software is tracking the car correctly.
The image processing must also be able to deal with glare on the road and not misinterpret double headlight reflection as 2 cars instead of 1. The image processing algorithm must be able to find the car at all hours of the day, the trickiest of these hours being twilight.